Okay, good morning. So this is our 18th lecture for the course Fluid Mechanics. Stop talking now. So in the previous lecture, we have been talking about the viscosity, vorticity, and while we discussed the vorticity, we found that it is nothing but 2 times of the rotation. Okay, angular velocity. So now I had given you 2 problems. So basically, we are having the 2 situations. In one of the situation, in both the situations, basically we are having nothing but from. If we look into the flow field, it appears that this is nothing but a rotational flow field. Okay, because the streamlines are forming the concentric circles. Okay, the difference between the two flow situations is that in first case I am considering that radial velocity is 0 and tangential velocity is omega into r. Okay, so it means all the layers of the fluids are rotating at constant angular velocity omega, and at whatever distance from the center a particular layer is located, if we multiply that with omega, that will be giving my tangential velocity. Okay, so in this case we are not considering any difference of rotational velocity between the fluid layers. It means this is nothing but identical to a solid body rotation. Okay, so the way solid body rotates, all the different portions of the solid body in radial direction moves at the same angular velocity. In the other situation, what I am saying is I am not calling it as solid body rotation, but I am giving the value of tangential velocity, which is nothing but equal to k by r, where k is some constant. So here you can see that our tangential velocity is inversely proportional to r. It means as we are moving away, so here tangential value of tangential velocity is actually decreasing. Okay, so what we have to do is we have to determine that out of these two fields whether these are rotational or irrotational. Okay, so what is the test for rotationality or irrotationality? If you recall from the previous lecture, I have given you the definition of rotational flow as well as the irrotational flow. Okay, so where our vorticity vector is non-zero, that will be rotational flow. Where vorticity vector is equal to 0, that is nothing but our irrotational flow. Okay, so out of these two flow situations, we have to now determine our vorticity vector. How we can determine the vorticity vector? Now this is a situation, so if you recall, whatever the formulation of vorticity vector I have given you in the previous class, that was applicable for Cartesian coordinate system. So that was in terms of x, y, z. Okay, so these two problems can also be solved with the help of Cartesian coordinate system, but then analysis will become a bit complex. So considering the nature of the flow, circular nature of the flow, we will try to solve this problem on the cylindrical coordinate system. So what I will be doing, I will be fixing the coordinate frame over here. So let us consider that this is nothing but coordinate r, and in this direction I have angle as theta. Okay, so this is my azimuthal direction, and then normal to the board I will be having nothing but z direction. So it means I have taken my in cylindrical coordinate system, I have taken the coordinates as r, theta and z. The benefit is that if I consider, so tangential velocity at every point in the flow field is actually changing. Okay, because it will be tangential to the streamline. Okay, but if I have to consider over here the Cartesian coordinate system, then it will be giving me two components of velocity. But in cylindrical coordinate system, I will be able to resolve with the help of a single component only, because along the direction in which this tangential velocity is varying, that I have considered as one of the coordinate over there. Okay, so now I have considered the r, theta and z directions. So corresponding to these directions, let us consider that E cap r, E cap theta and E cap z, these are nothing but the unit normal vectors in r, theta and z directions. Okay, so once we have these unit normal vectors, now what we have to do is actually we have to determine the vorticity vector. We know that vorticity vector is nothing but, what is vorticity vector? Sorry, I defined with the capital omega. So vorticity vector is nothing but del cross v vector. Okay, now this del operator, because I am talking about the cylindrical coordinate system, so in cylindrical coordinate system my velocity field will become Vr times E cap r plus V theta times E cap theta plus Vz times E cap z. So that will be my velocity vector. So if I am considering the cylindrical coordinate system, then of course I have to use my del operator also in the cylindrical coordinate system. So how we will be obtaining the del operator in cylindrical coordinate system in more details, that I will be talking later in later lectures. For now, you can just recall that in cylindrical coordinate system, it will be nothing but equal to del by del r of E r cap plus 1 by r del by del theta of E theta cap plus del by del z of E z cap. Okay, so this is my del operator in cylindrical coordinate system. How to obtain this? Later on, whenever we will be finding our governing equations, particularly using the differential fluid element, then at that time I will try to show you at least one case with the cylindrical coordinate system, so that we can know how this del operator is coming. Okay, but for the time being, you can just remember this, so that this is the del operator in the cylindrical coordinate system. So now if this is the del operator, then can you tell me what will be the vorticity vector now? So for vorticity vector, we have to consider E cap r, E cap theta, E cap z. Then del operator is del by del r, 1 by r del by del theta, del by del z. Then this is Vr, V theta and Vz. Is this point clear? So please take this cross product and tell me what I will be getting. So if I do so, from here I will be getting that my vorticity vector is nothing but E cap r times, please tell me, 1 by r del Vz by del theta minus del phi theta by del z, okay, minus of E cap theta into del Vz by del r minus of del by del z Vr, correct, plus E cap z into del by del r V theta minus 1 by r del by del theta of Vr. Fine. Okay. So now if I little bit modify this, so I will be getting that first term I will be keeping as it is. Okay. In second term I can make it plus sign, and then it will be becoming del Vr by del z minus del Vz by del r, and in third term if I take 1 by r common, then it will be becoming E cap z 1 by r times del by del r of r v theta minus del by del theta of Vr. Fine. So now this is my vorticity vector in nothing but the cylindrical coordinate system. Okay. So the flow situation which I have considered over here, you can see this plane is in r theta directions. Okay. So vorticity vector will be in the normal plane. So it means vorticity component which will be applicable over here, that will be nothing but the z component for this type of flow field. Okay. So z component of vorticity, if you see, so z component of vorticity is 1 by r del by del r of r v theta minus del Vr by del theta. Okay. So now if I calculate this for the first flow field, which is equivalent to a solid body rotation, for that Vr equal to 0 and V theta is equal to omega times r. Is this point clear? Omega times r. Now let me substitute it over here. So what I will be getting ultimately, I will be getting that omega z is equal to 1 by r times del by del r of omega into r square. Anything important going on? Ask him. Anything important going on? Because here I can see your voice. Okay, so omega z will be 1 by r del by del r of omega r square minus 0. Okay. So from here I will be getting that omega z is nothing but equal to how much? 2r omega. So ultimately 2 omega. So for a solid body rotation, we have the positive value of omega. Fine. So from here, I will be getting nothing but what I will be getting? Non-zero value. So if this is non-zero, so it means solid body rotation is identical to a rotational flow. Okay, this point is clear because here vorticity vector is coming as non-zero, so this is nothing but a rotation. Okay. If I talk about the second situation now, so in case of second situation, what we have? In case of second situation, we have once again Vr equal to 0, but our V theta is equal to K by R. Okay. Now if I substitute over here, then omega z will become 1 by R times del by del R of R times V theta. R times V theta will become only K, because K by R into R, that will cancel, minus 0. So ultimately I will be getting omega z is equal to 0. So if it is 0, it means my flow field is irrotational. Okay. So one important conclusion we made from here, that even though in both the situations our streamlines are looking to follow the circular path, but it does not mean that the flow is rotational. Okay, so we should not go into visualization, but we should quantify it in terms of the vorticity vector. Okay, because if we look visually, it is appearing that flow is taking a circular path, so it must be a rotational flow. But ultimately, whenever we are trying to find the vorticity vector for this, it is coming out to be 0. So it means this is nothing but an irrotational flow situation. Okay, so what is the difference? In case of boundary layer theory, where the flow is actually moving in a almost in a straight line. Okay, two-dimensional flow over a flat plate. So there I have shown you that there also rotation can come. So similarly, in a circular flow also we can have irrotational flow situation. Okay, so typically what I will be observing that if I have a flow particle in this type of rotational flow field, say at any point this flow particle is having this orientation. So this long tail I am keeping just to show the orientation over here. Okay. So whenever this flow particle will keep on rotating about this field, its orientation will also keep on changing. Is this point clear? So rotational, this one, orientation of the flow particle is changing. So it means in rotational field, flow particle is actually rotating. On contrary, if I talk about the irrotational flow, here if I have flow particle, this flow particle at all the instances will be having the same orientation. Okay. So this is nothing but identical to the situation of a Ferris wheel. Have you seen Ferris wheel? So there when a person is sitting, they always remain in the vertical orientation, top to down. Okay. But wheel keep on rotating. So that is nothing but identical to this particular second situation of irrotational flow. On the other hand, if you talk about merry-go-round, so that keep on rotating and orientation of the person also keep on changing with the rotation. So that is nothing but kind of a rotational flow situation. Okay, is this one clear? Now, whatever I have done over here, I have shown you people one situation and then we tried to find it whether it's a rotational or irrotational. So similar type of situations you may expect in your exam also, that some velocity field or some flow field is actually provided to you and you have to determine whether the flow is rotational or irrotational. Okay. Now we will once again come back to this rotational and irrotational flows, particularly when I will be talking about in more details on stream functions and velocity potential functions, but that part will come later. So once again we will come back to this rotational and irrotational flows. Okay. So for the time being, now we will try to quickly define one more parameter which we call as nothing but our circulation. Okay. So circulation is nothing but the definition of circulation is if I have a closed curve, any closed curve, and say the length of any element over this closed curve is dl. Okay, and velocity at this point is say v. Okay, so if I take the product of v vector dot dl and if I do its integral over the closed curve, so I am putting over this integration a circle, that it means I am putting a cyclic integral, closed curve integral. So that is nothing but defined as circulation, and it is given by a symbol capital gamma. Okay, so the meaning of circulation is clear. The way we are defining vorticity, we are defining rotation. Similarly, one more important parameter is there, which we call as nothing but a circulation. Okay, so what is circulation? I have any closed curve in the flow field. If I draw any arbitrary closed curve in the flow field, okay, and over that closed curve, if I take any element of length dl and say corresponding to that element length dl, I have velocity v. Okay, so now if I take the v vector dot dl and if I do the circular integral of that over that arbitrary closed curve, that will be giving me circulation about that particular closed curve. Okay, so now how we can analyze this situation? So let us consider a two-dimensional fluid element, and let us assume that this fluid element is having u velocity at this point, and at this point velocity, if delta x is its length in this direction and delta y is length in the y direction, then here velocity will be u plus del u by del x into delta x. Okay, similarly here, say this is v velocity, and at this point velocity is v plus del v by del y into delta y. Okay, so over here we have to consider one thing. When we are considering this dl vector and v vector, we have to keep velocity and our length vector as nothing but parallel to each other. Okay, tangential to each other, because then only our dot product will be coming out as non-zero. If I consider perpendicular, then dot product will become zero. Okay, so for this situation, if I define for this fluid element circulation vector, then what it will be? In this direction, how much is the velocity? U velocity is there in this direction. What is tangential velocity? U. Okay, so it will be becoming U times delta x. Fine. Then in this direction, what is tangential velocity over here? V plus V times, sorry, tangential velocity is V, or is it V plus del V by del x into delta x? Because this is my origin over here. So here tangential velocity will be, this I have written wrongly. Please make this correction. So here velocity is u. So at this point velocity will be u plus del u by del x into delta x. Similarly, if I talk about velocity v, so at this point velocity v will be nothing but v plus del v by del x into delta x. Okay. So ultimately from this side I will be getting v plus del v by del x into delta x. Is this point clear? Then here what will be velocity u? Here velocity u will be u plus del u by del y into delta y at this face. So this is the tangential velocity to this face, but this tangential velocity and this length vector is having opposite directions, because I am taking this path, this way I am moving. Okay, so here this is the length vector and this is the velocity, so both are in opposite direction, so I will be putting a negative sign. So minus u plus del u by del y, sorry, along with this delta x I have to also put delta y. Why this delta y is coming? Can anyone tell me? This is nothing but a velocity. Velocity we have to multiply with the length, so length is delta y over here. Okay. So u plus del u by del y into delta y is our velocity, and how much is length? In this direction length is delta x. Point is clear? And then from here I have v velocity and length is in the opposite direction, so I will be writing minus v times of delta y. Okay, so now out of this if you do, so you will be finding u delta x will cancel, v delta y will cancel, so I will be having del v by del x minus del u by del y times delta x delta y. Is this one clear? Point is clear? So what is this? Del v by del x minus del u by del y. Omega z. This is nothing but omega z. Omega z times delta x delta y. What is delta x delta y? dA, area of this fluid element. Okay. So now if I write circulation, which will be nothing but integral of d circulation, so ultimately I will be getting that cyclic integral of v vector dot dl vector is becoming equal to integral of, what is the integral of this? This is nothing but my omega vector. So omega vector will become, okay, let me write first as a omega vector. Omega vector dot dA. Okay, so ultimately this omega vector into dA vector can also be written as integral of del cross v vector by dA vector. Okay, so it means that circulation, which is nothing but a velocity vector dot dl vector, which is a line integral. Okay, which is a line integral that can be written as delta cross v vector into dA, which is nothing but a surface integral. Okay, so a theorem which connects the line integral and the surface integral, that is called as Stokes theorem. So this is nothing but directly I can write from this point to this point, directly I can come with the help of Stokes theorem also. From vector calculus, if I use the Stokes theorem, then directly I can convert this line integral into a surface. Okay, so this is how we define nothing but the circulation in the flow. So what the question you may expect is that some velocity field is given and you have to determine the circulation for that. So for determining circulation, you have to choose whichever way becomes easy for that problem. For example, you can use this line integral also, or you can first determine the vorticity field and then apply this one. Okay, so that will be depending upon the problem. Problem to problem, you may have to use different strategies. Okay, is this one clear? So this is this was another important factor which is related to fluid kinematics. Now we will stop for fluid kinematics and then we will start our discussion on the dynamics part. Okay, so now we will be referring to fluid dynamics. So whenever we are talking about the fluid dynamics, basically we have to also include the effect of forces on our flow. Okay, so in case of fluid dynamics, we can take two approaches. First is integral approach and second is differential approach. Okay, so in integral approach, what we will do, we will try to find out some integral form of the governing equations, and these we will try to apply for a situation which is under consideration. And in case of differential approach, we will try to go for the differential equations, our governing equations will be nothing but in the form of partial differential equations, and then we have to solve these partial differential equations in order to find the flow field. Okay, so typically in two approaches the major difference is that when we refer to the integral approach, we consider our fluid element of finite size. So we consider a finite sized fluid element, and when we consider the differential approach, here we refer to, say this is my finite sized element. Inside this finite sized element I will be referring to a very small, infinitesimally small fluid element. Okay, so here I will be having infinitesimally small fluid element. So the difference is that whenever I am talking about the finite sized control volume, I will be looking on the properties as a whole. Okay, and there may be variations of properties within this particular finite sized volume, but ultimately we will be referring to the unique representation in terms of the integral. Okay, on contrary, whenever I am talking about this differential approach, here our approach will be that whatever the solution we are actually obtaining, that solution is applicable at each and every point within the flow. Okay, so our governing equations in such a way we will be deriving that ultimately we get the solution which we can determine at each and every point within the flow. So it means this will be giving us nothing but a detailed continuous solution out of this. Okay, is this point clear? So in case of integral approach, what we refer, we take kind of whenever we will be further analyzing the systems, then you will be analyzing, then you will be understanding. For example, the approach which we follow in thermodynamics. Okay, so in thermodynamics you all might have done steady flow processes. So in steady flow processes what we do? We define at a phase a constant value of the velocity, and we say that this is nothing but the average value of the velocity which is entering at the inlet, average value of the velocity which is going at the outlet. Okay, and at the entire inlet or entire outlet, all other fluid properties such as enthalpy, internal energy, entropy are remaining constant. Okay, on contrary, in real scenarios you will be finding that because of the viscosity of the fluid, if you are having a pipe inlet, then velocity cannot be same at every point. Okay, near the wall velocity will be 0, at the center it will be maximum, and at other places it will depend upon its location in the detail plane. Okay, similarly you may have a situation of variable properties. For example, if you are having a heated system, so one end of a pipe is at high temperature, other end of the pipe is at low temperature, and a fluid is flowing inside that pipe. So you know that fluid properties such as density, viscosity, surface tension, these are nothing but the function of temperature. So you will be finding that in some portion of the pipe the values of properties are different, and in other portion values are different. Okay, so whenever we are trying to accommodate such issues into our mathematical analysis, then our approach will be becoming more involved and more complex. Okay, so that is something which we call as the differential approach. Okay, so in case of differential approach, we try to consider the variations at each and every point within the flow. So that's why whatever the solution we will be obtaining, that will be also giving us the values of flow parameters at each and every point within the flow grid. So this is a more involved approach, but the issue with this approach is that this is very complex to solve. So for very simplified situations only we will be able to find the analytical solution, otherwise we have to then go for the other techniques such as numerical solution for the detailed solution of the equations. Okay, how to do that we will be seeing in the subsequent lectures, but integral approach is the most easiest one, because here we consider a finite sized volume and then we try to determine the parameters as a whole. Okay, so let's see, but still don't consider that it is as easy as we have studied in thermodynamics to analyze the different flow situations. Here little bit of complexity will come because of the fluid flow. Okay, so now whenever we will be applying these two approaches, or if we apply any approach, it is, I think, well clarified in the thermodynamics that we have to first consider what is the system or the area which is under observation. Okay, so in thermodynamics you might have talked about two approaches. One is system approach and other one is control volume approach. All of you know about these two approaches, system approach and control volume approach. Okay, so what happens in system approach? Anything which we want to analyze, we put inside a real or imaginary boundary. Boundary can be either real or imaginary, any boundary. Okay, and everything inside that boundary we call as our system, and outside we call surroundings. Okay, and we consider that through this boundary there is no interaction of mass. So mass interaction is not there, but only interaction which is possible in two sides, that is energy interaction. And energy can interact either in the form of heat or work. Okay, so that is something which you have studied. Then second approach you study is that we consider a boundary. Now across this boundary, mass can also come and mass can also go. So I can have some M inlet or energy inlet, and I can have M out and energy out. Okay, but in this approach we have fixed ourselves in certain region and we are interested to determine the properties in that region only. Okay, we are not concerned inside or outside this region. What is happening, we are not at all concerned about. Okay, but whatever the fluid portion is inside this control volume at any instant, we just are interested in that. Fine. So the difference is, in first case, because no mass can enter or go out of this, so whatever the mass we have taken initially, its identity will always remain the same. But in second case, identity of mass will not remain same, but it will keep on changing. Is this point clear? So our interest is at whatever instant we are trying to determine the flow field, whatever mass is there inside this control volume at that instant, we are only interested in that part. Is this point clear? Okay. Now, whenever we have to analyze any situation, then what we have to do? We require some governing laws. Okay. What we require? We require some governing laws. And typically, if you see, all the governing laws are kind of developed initially for a fixed quantity of matter. Okay. So, say I am using a system approach. So what I will be doing, say if I have a system, then the very first law comes is conservation of mass. Okay, and as per the conservation of mass, I will be talking about mass of the system. Okay, and if I am referring to the system approach, in system approach what will be happening, even if I go at any point of time, because no mass is crossing the boundary, so ultimately my dm system divided by dt will be equal to 0. Okay, dm system divided by dt will be equal to 0. There will not be any change in mass of the system with time. This point is clear? Then second law we can talk about is Newton's law of motion. So here what we will be having, as per this law, if I have to determine force, that will be nothing but mass of system into acceleration. Okay, and that can also be written as mass of system into d by dt of v vector. Okay, and ultimately it can also be written as d by dt of mass of system into its velocity vector. Okay, so that is nothing but rate of change of linear momentum. Fine. Similarly, I can have, if I want to calculate movement, okay, torque, movement, then movement vector will be equal to nothing but rate of change of h What is h? Angular momentum. Okay. Movement is nothing but rate of change of angular momentum. Force is equal to rate of change of linear momentum. H is equal to rate of change of. Okay. And what is angular momentum? Angular momentum will be coming out to be position vector cross velocity vector times dm and integral of that. Okay. Fine. Or if I have discrete set of masses, then rather than integral I can put actually summations. Okay. Then similarly, what next I will be having? Third important governing law. First is mass conservation, second is momentum conservation. In momentum conservation I have included both linear momentum as well as the angular momentum. And third one is energy conservation. Okay. And what is energy conservation for the system approach? First law of thermodynamics, that is nothing but the energy conservation. Okay. So first law of thermodynamics tells us del Q minus del W is equal to dE. So this is my third important law. Okay. Of course, whenever I will be talking about the fluid flow, I have to consider this law in rate form. But at the moment for a system, if I have to apply, then ultimately I can write del Q minus del W equal to D. Is this one clear? Then apart from that, what another general law will be coming? Another generic law is second law of thermodynamics. What does it tell? Have you studied second law of thermodynamics? Okay, not yet. So second law of thermodynamics, important finding, you will be finding that ds, where S is entropy of the system, that is greater than equal to del Q by T. So you will be studying now in your course. Okay. So whatever the laws which I have listed over here, these are nothing but called as the generic laws, universal laws, which will be applicable for any system. So laws can be defined in two ways. Few are the generic or universal laws and few are the particular laws. So particular laws are applicable for specific situations. These cannot be generalized for all the situations. For example, if you talk about Fourier's law of heat conduction, that will be applicable only where the conduction heat transfer is taking place. Okay. Similarly, Newton's law of cooling, that will be only applicable where the mode of heat transfer is convection. So these are situation specific. But if you talk about first law of thermodynamics, second law of thermodynamics, conservation of mass principle, conservation of momentum principle, you will be finding out that whatever system you consider in this universe, no system in the universe can exist without following these laws. Is this one clear? So now, for system approach, we know these laws are very easy to determine, but ultimately, whenever we will be considering the flow of the fluid, we cannot always consider that, okay, I have a fixed parcel of the fluid and I keep on following that fluid parcel. That is not always possible. Okay, we have already discussed that if we go for this type of system like approach where identity of the fluid is not changing, then we have to consider the Lagrangian approach, and to implement Lagrangian approach at the engineering level is actually not practically possible. Okay, so that is the reason, because number of equations which we have to solve, these will become extremely high. Okay, so that is the reason majorly we refer in fluid flow our Eulerian approach, where we fix the control volume, and within that control volume, what is our control volume? That is nothing but our region of interest. Okay, and in that control volume only we are interested in finding the variations in flow parameters. Okay, but while these variations will be taking place, identity of the fluid will not remain fixed. Okay, fluid will keep on entering and it will keep on going out. So whenever we are talking about the control volume approach, then, but all the governing laws which we have studied till date, all we have studied nothing but for a system approach. Okay, so we have to devise some way which can convert the governing laws from system approach to control volume approach. Is this point clear? What I am trying to say over here. Okay. So all the governing laws which I have defined just now, these are nothing but applicable for the system approach. But ultimately, whenever I will be doing the analysis of the fluid flow, I will be using the control volume approach, where identity of the fluid is not remaining constant, but laws are defined for fixed identity of the fluid. Okay. So ultimately, we have to devise something which can convert these governing laws from the system approach to the control volume approach. Okay. So the theorem which converts system analysis to control volume analysis, that particular theorem is called as Reynolds transport theorem. Okay, so a theorem which converts system analysis into the control volume analysis, this is very important theorem in the fluid flow, because whenever we will be talking about fluid mechanics, we have to always consider the control volume approach. But our governing laws are already readily available in system approach. Okay, so somehow we have to consider these convert these governing laws from system approach to control volume approach. So this can be done with the help of the Reynolds transport. Okay, so before going to the Reynolds transport theorem, let us first understand that what type of different control volumes we can have. Okay, so say I have an airfoil structure, and this airfoil structure is actually moving in the flow field. So if it is moving in the flow field, then ultimately what will be happening? Whatever the fluid surrounding it, it will interact with this solid object and it will try to create some sort of, or basically this solid object will do some changes in the fluid surrounding it, and fluid will also create certain effect on this particular solid object. Okay. So now, in order to analyze the situation, I have to define a control volume over here. So what I can do, I can consider a region of arbitrary shape, and this I can define over here. Why I have defined control volume only up to this distance, or only up to this distance in this direction? Why not beyond that? You will be finding that when aeroplane is moving, okay, so a significant portion of the fluid above, below, or front or back of the aeroplane is actually getting affected. But if you move very far away, there you will be finding that flow field is actually completely undisturbed. Okay. So while we are choosing the control volume, we have to choose the region where mostly changes are happening within the flow. Okay. And where changes are not happening, then that portion is actually not is of our interest. Okay. So whatever the quantity which we want to just analyze, that we will be keeping it over. Okay. So now if we talk about the control volume approach for so this is, I will be calling as a control volume, and the boundary of this control volume is called as control surface. So boundary of control volume is nothing but my control surface. Okay. So now in this situation, what will be happening? Because my interest is aeroplane, and aeroplane is always moving. So if aeroplane is moving, I have to move my control volume also with the aeroplane. Okay. So this has become nothing but the case of a moving control volume. Point is clear? Because I am interested only to analyze the region just close to the aeroplane. Okay. Similarly, I can talk about ship. If say ship is flowing in water and I want to analyze the flow field around the ship, then I will be fixing a control volume around the ship, and when my ship is moving, then ultimately my control volume has also to move. Okay, so this is the case of a moving control volume. Then I can have another situation. Say I have a circular pipe which is fixed and fluid is flowing through this pipe. So now what will be happening? I am interested that how interaction between the fluid and the pipe is taking place. So in this case pipe is fixed. So now whenever I will be choosing a control volume over here, so say this is my control volume. So now this control volume is actually fixed in space. Okay, so this is a fixed control volume. Fine. Is this one clear? Then I can have third situation. If I talk about a reciprocating compressor, if I want to analyze a reciprocating compressor, it will be having one inlet valve, it will be having one outlet valve, and it will be having some piston which is taking air in and then pressurizing it and sending out. Okay. So in this reciprocating compressor, what will be happening? Once again, my interest is actually fluid region. Okay. So fluid region, if it is of my interest, then this I will be taking as control volume. Okay. When piston is moving down, then size of the control volume is actually increasing. And when piston is rising up, then size of the control volume is decreasing. So now this type of control volume I can say as deformable control volume. Point is clear? And then I can also have a combination of motion and deformation, where I am having a moving as well as a deforming control volume. Okay. So these are the different situations which we will be experiencing while analyzing the fluid flow problems. Okay. So now what we will be doing for all these different control volume situations, one by one we will be considering, and we will try to utilize the Reynolds transport theorem to convert properties from system approach to control volume approach. But while we will be doing this, then we will be considering four different types of control volume combinations. Okay. So in the next lecture we will talk about Reynolds transport theorem.
So what